Okay, hopefully now you should all see marine ecosystems, dynamic and fluid. Could someone just give me a shout out? Yes, I see that.
Yes, we can see it.
Excellent. Bonus.
Yes.
Now, if I draw on the screen like this, can you see my red scribbles?
Yes.
Yes.
Even better. Good. Okay, so far so good. Well, welcome to our first Google Meet. I'm just going to run through a bit of a presentation, which I, as I mentioned earlier, have literally just thrown together. And we'll have a bit of talk about a couple of concepts as we go through this presentation. But I want to talk about the very dynamic and fluid nature of marine ecosystems. They're quite different from land-based ecosystems. Land-based, we can say terrestrial. So if you ever see the word terrestrial food web or terrestrial ecosystem, it just means that on land. Okay, now marine ecosystems are different in quite a number of ways. So let's jump into it.
So should we be taking notes on this?
That's a very good question. You could, if you want, by all means, have a pen and paper next to you. That's cool. I am currently recording this Google Meet, so this will go on the classroom later on today, so you can always refer back to it then. But absolutely, I'm not going to stop you taking notes if you want. I'm also not going to make you. I'm not going to make everyone show me that they've got out their pen and paper. So I'll leave that up to you. But yes, it's always a good idea.
Thank you.
But no worries. Here we go. Right, and we're underway. What we see here is a food chain. One very small, brief example of a marine food chain. There are so many out there. This is one quick example. So we start with the phytoplankton. Remember, the phytoplankton are the little plants, teeny tiny little microscopic plants. They could get eaten by zooplankton. I know it looks like zoo. Yeah, it looks like zooplankton, but we say zooplankton. And they are essentially the teeny tiny little microscopic animals. So the little plants get eaten by the little animals, which get eaten by bigger animals, in this case the fish larvae, and then the fish, and then the shark further down the food chain. So what we can do here, let's just talk about trophic levels. Now, some of you may have come across this term before as trophic level when you've done food chains and food webs in the past. Trophic level is essentially the level, the position that the organism has in the food chain. Troph is to do with food. Okay, remember, we often come across words that if we break it down, we can work out what it means. Well, troph means food. So a trophic level, think of it as the food level. So phytoplankton would be the first trophic level. Zooplankton would be the second trophic level. Then we have the third, the fourth, and the shark is the fifth trophic level. Okay, so that's what trophic level means, just the position that the organism sits within a food chain or food web. Now, we'll come back to this in a little bit to see how the trophic levels can actually change for different organisms. But let's just look at another example of a little food chain. Once again, we're starting with phytoplankton. That is the first trophic level. And then we go to crustacea for our second, gets eaten by a fish for our third trophic level. A dolphin ate the fish, so there's the fourth trophic level. And an orca ate the dolphin. That's unfortunate, but that is the fifth trophic level. Of course, orca, killer whales, a lot of people often call them, they are actually dolphins, aren't they? So that's a dolphin eating a dolphin. So there you go. Orca are actually dolphins. But anyway, there's another example of a food chain. And we have one more. This time we've got our primary producer, so that's our phytoplankton. We have the first trophic level, second trophic level, third trophic level, fourth trophic level, and up to the shark at the top for the fifth trophic level. So do we have this idea of trophic level? Are we happy with that? Just the position of a food chain? Anyone give me a shout out?
Yes.
Yes.
Yep.
Yes.
Cool. Excellent. Now, it's not this simple. What we've been looking at so far is just some little simple food chains. It's not that simple because what we actually have is more of a web. So a food web, this is what we're looking at now. Food, I'll just scribble sometimes on the screen where I have something to scribble. A food web is essentially lots and lots of food chains put together. Okay, not just food chains sitting next to each other, but interlinked. So we could pull out any food chain we want from here. Let's start with phytoplankton. Okay, that's a good place to be for the first trophic level. Okay, so they're the plants, they're the producers, they're the ones converting the sunlight energy and making sugars. So, just like terrestrial food chains and food webs, they start with plants as well, doing photosynthesis. That's what the plants in the ocean are doing. These phytoplankton are still doing photosynthesis. So they are the organisms that still start off the food webs and the food chains. So we could have one food chain which goes from the phytoplankton to the fish, maybe down to the shark, and then maybe, unfortunately, the shark got caught by people, and that goes up to the person. So for that food chain, we have the first trophic level, the phytoplankton, the fish is the second trophic level, the shark is the third trophic level, and the person is the fourth trophic level. That is just one example of a food chain that we could have pulled out of this food web. We can pull out a number of different food chains. Maybe instead of going down to the shark, we're just going from the phytoplankton to the fish and then up to the person. We've only got 3 trophic levels. Or maybe we're going from the phytoplankton and we're heading off to the left, and we can start here, go to the mussels, and then to the person. Again, 3 trophic levels. Or maybe the mussels get eaten by an octopus, the octopus get eaten by a shark, etc. So you can see, hopefully, that we can, from a food web, we can pull out lots of different food chains. Okay, so a food web is essentially a lot of food chains, but they're interlinked. All right, so that shark, that could be eating the octopus or the starfish or the fish. All right, oh, starfish, that's unfortunate. Let's just know that a starfish is properly called a sea star. So most people will call them starfish, but actually they are called sea star. But, not my diagram. I didn't make it, so I guess I can't complain too much. But let's do some, on the side learning as we go. Yeah, we now know about sea stars. So that's the food web and trophic levels. Okay. Now, on land, this is what we often have. This is called a food pyramid. Now, terrestrial food webs are often described as being like pyramids because they start at the bottom. We have lots and lots and lots of plants, right? In this case, the plant is grass, but we've got lots and lots and lots and lots of them. And then they get eaten by herbivores. So here we go. Now we've got less of these guys. And as we go further up the pyramid, they get eaten by these here, but we've got less of those, and they get eaten by this bird up here, but we've got even less of them. So this was described as a pyramid. We talk about the food pyramid because we've got the most organisms are at the base. Okay, you've got to have lots and lots of plants to feed the organisms above and then above and then above. Okay, now the reason for this to make sense is that when we have a food chain, let's just go back to a random food chain, you'll note the arrows are drawn from what gets eaten to what does the eating, right? So we're going from the phytoplankton here to the zooplankton. The arrow goes that way. That's because what we're actually showing is the energy transfer. The energy from one organism, when it gets eaten by something else, that energy gets absorbed into the second organism, okay? So we're not saying this eats that, we're saying the energy moves from this organism to this other one. But actually only, oh, what happened there? Hang on, technical issues, there we go. Actually only 10% of the energy gets transferred along the way. So it should kind of make sense when we look at this food pyramid, why there might be less of the higher organisms, because we're only getting 10% of the energy each time. So we can see these producers down the bottom, lots and lots of them, they had 1,000 kilocalories. Kilocalorie is just a unit of energy, right? So in terms of the energy units, they had 1,000. But then the next step up, they only had 100 of those units, and then there's only 10 of those units, and then there's only 1 of that energy unit. So we're not passing all of the energy through the food chain. Only 10% goes through each link. So it kind of makes sense, really, hopefully. Well, it makes sense to me. Hopefully it makes sense to you, that there would need to be many more producers. There has to be 1,000 of these to give the 100 of these the energy they need, which can then give the 10 of these the energy they need, and then the 1 of these the energy that it needs. So that's sort of a terrestrial or a land-based ecosystem idea. We describe it as being like a food pyramid, and hopefully that makes sense to you. If this were a marine ecosystem, we would look something like this. Okay, so again, we're starting with the phytoplankton, going up through the zooplankton, and then through some fish, and then maybe some tuna or a shark. But at each time, so we're going 10%. We start with 1,000 to 100 to 10 to 1. This is what this food pyramid might look like for a marine ecosystem. That would be lovely in theory, but what we actually find is that there are so many marine ecosystems where we have an inverted pyramid. The pyramid flips the script, and we actually end up with something like this. Actually, I just showed you the picture there. That's just a photo of zooplankton. I love this photo. That's the, what am I saying? Zooplankton. No, it's not. That's the phytoplankton. They're the little plants in the ocean doing photosynthesis, right? Tiny little microscopic plants. But what we actually have in a lot of marine ecosystems, the pyramid is upside down. So we start with our producers, that's the phytoplankton that we just saw, but there are less of them, less total biomass. What we're talking here is the total biomass, basically how heavy is the total number of these organisms. Now, as we saw, we needed to have lots of those producers, lots and lots and lots and lots and lots of them, to supply enough energy for the next layer, and then that enough energy for the next layer, and then the next one. But in the marine ecosystem, we have an inverted pyramid. We have a lower total biomass of the producers than we do of the herbivores. And then the carnivores have even more biomass. That just seems a little strange. What could be going on here? Well, what is going on is that these phytoplankton, sure, we don't actually have very many of them, and that can't seem logical that it could possibly support the food chain and the food web above it, but they are very short-lived. So their lifespan is measured in days compared to land plants, which is generally measured in years. Your tree lasts for years. But the phytoplankton, they only live for days at a time, okay? So at any given moment, there is less of the producers, less of the phytoplankton than the higher organisms, which doesn't make sense, but there is a very rapid turnover. So at any given time, there's less of them, but because they have a short lifespan, but the turnover is so great, the turnover is so rapid, that actually leads to there being enough total biomass to support these higher organisms. So if you just glance at the pyramid, it wouldn't seem like that. You'd think, oh wait, that's not enough producers to support all the herbivores, and that's not enough herbivores to support all the carnivores. Okay, but because we have shorter lifespans and a more rapid turnover, it actually does work out. So it's quite a unique feature of marine ecosystems that the food pyramid is actually flipped. It's upside down. We talk about an inverted food pyramid in a lot of marine ecosystems. Right, so let's see what we have on here. Okay, here's another picture. This is talking about the complexity of the marine food webs. Because not only is the food pyramid flipped upside down, and it doesn't seem to make sense unless you consider the rapid turnover of the lower organisms, but the food webs are very, very complex in so many marine ecosystems. Right? So many marine ecosystems might consume food at different trophic levels at different stages of their life. A lot of marine animals are generalists because you might take it for granted, but you're probably going to have dinner at about this certain time each day. Well, the fish doesn't know when its next meal is going to come along, right? So they have to be generalists. Basically, they're not picky eaters. If something comes along, they will just eat it because they don't know when their next meal is going to be, right? Sometimes we have one species which is both predator and prey of another species. So here we have, in this photo, we have a squid. Now you'll notice he's in the middle of this food chain because this adult squid is a predator of this larval bluefish, basically this small bluefish right here. So if we were making this into a food chain, we would put the arrow this way because we're showing the energy movement, right, from this small bluefish into the squid. However, when that bluefish is an adult, it actually turns around and eats the squid. So that didn't work. Hold up. There we go. So with this very simple food chain, we've got a squid and a bluefish, but the squid eats the baby bluefish. But if the baby bluefish doesn't get eaten when it grows up, is now an adult bluefish, it actually eats the squid. So, you know, we've got one species, in this case, the squid, is both predator and prey for another species. So we've got a lot of complexity in marine food webs, right? Now, we're talking about marine ecosystems being very dynamic and fluid. It's not just about the food webs and the food chains, okay? So here is another little fish. Now, this guy's happily swimming along. Who is going to tell that fish, stop, you're not allowed to go over there, right? No one's going to say that because in the ocean, funnily enough, we don't have many of these. We don't have fences, okay? So many species move to new locations, some swimming huge distances. You know, they might be in pursuit of food or a good habitat, showing habitats, right? Many fish species move to new locations with a different stage of life. Maybe they're part of their reproductive cycle, maybe different seasons, maybe a change in food supply. So, you know, we don't have fences in the ocean, right? So the traditional boundaries between regions or between habitats, they don't really exist in the ocean. Now, here's an example. These are blue whales, these beautiful creatures right here. These are blue whales. Now, blue whales can actually travel about 5,000 kilometers from their spawning ground to the best feeding grounds. They actually like to feed up near the Arctic area and those polar waters, very rich in food supply. So what the humpback whale does when it gets there is they actually blow bubbles. It's called bubble netting. It's quite a fantastic way to feed, but this bubble netting, what they do is they blow lots and lots of bubbles and they swim in circular patterns, obviously, you know, underneath the surface of the water. Now, what this does is traps the fish inside these rings of bubbles. So the fish don't sort of like passing through the bubbles that are coming up from below. That sort of freaks them out, so they all huddle together. And then, of course, what the humpback whale does, not just the one humpback whale, we have lots of humpback whales all doing this, and then they just open their mouth and swim upwards. So this is bubble netting. We can see here the bubbles from the spiral there, and then we have a number of humpback whales emerging, you know, breaking the surface with the mouth open and just taking in all the fish in one go. So here's another photo. It's quite a fantastic way to feed. They work in a group. They blow lots of these bubbles, bubble netting. They trap the fish, then they move upwards. So these humpback whales have actually swum about 5,000 kilometers in order to get into these Arctic waters where there's this great food supply. Okay, so marine organisms can travel huge distances. Another example here, this is a hawksbill turtle, highly endangered. Now, a few years ago, I took a number of students to Vanuatu. I've done this a couple of times, and we sponsored the tagging and release of these hawksbill turtles. So there is one there, and then we put them on the beach when they were ready to go, you know, back to the sea. Now, why couldn't we just return them back to the sea? Well, actually, you can't do that. You put them on the beach, and then you let the turtle find its own way down to the water. And there he goes. Now, the reason for this is that a lot of sea turtles, well, the female sea turtles, they've been known to paddle over 1,000 kilometers to return to the exact same beach of their birth to lay their eggs. Okay, so the female hawksbill turtles, they need to find their own way to the water from the beach so that they can return to the same place. All right, so, you know, this long-range mobility of marine species is just a huge challenge for scientists trying to observe and monitor populations of marine organisms, all right, it just presents a big challenge for us trying to do that. But that just shows the very dynamic and very fluid nature of the marine ecosystems. Now, actually, if we just go back up, one thing I should have said about this inverted food pyramid here, because we've got fewer producers at any given time, but remember it's a rapid turnover, so they are able to supply the energy needed for the higher organisms. But this actually means that if there's any interference, we could say, with the food web or the food chain, if there's any issue that could be more disastrous than issues on land. Okay, if that makes sense. Hopefully that makes sense. Because we don't have as many of them, any challenge to the food chain could be, like I say, more disastrous to the other organisms. Okay, so a bigger issue in the marine ecosystem than a challenge to the food chain for a terrestrial ecosystem. Okay, right, so that, I guess, wraps us up. We are nearly due to finish this Google Meet anyway. So there's a quick look at the marine ecosystems, at the very dynamic and fluid nature of them.
Don't forget to subscribe. And like and comment.